Hello everybody and welcome to this video where I want to explain a bit more how Tesla's new architecture will work, and I want to jump more on like the article that I wrote that had fantastic results. This article worked really well, and in particular because it explained a lot um, what people were wondering. So now it talks about the planning systems. I really think you should probably read it before watching this video, talking about architecture in 2021, 2022. I'm going to do a recap here, so you actually don't have to go and read it. I'm going to do a recap and then uh, dive into three things today. So number one is the recap, like understanding Tesla's architecture until 2022, 2023, like today. Then we're going to see some end-to-end training. And finally, I'm going to answer some questions I had. So let's get started with this. And so I'm going to jump into this line from 21 to 23 and beginning with 2021. So the main idea of this year was that they introduced an algorithm that they call the HydraNet. And the HydraNet, like I have a course called HydraNet. So it's something that I really love at the point because you have tons of images and you have tons of different tasks. Like you need to detect landlines, you need to work on object detection, depth estimation, semantic segmentation. It's like you can have 20, 30 different tasks just on vision. And with a HydraNet, you can have one backbone and then just have heads that solve the specific task. So the actual HydraNet from Tesla is here. And you can see from bottom to the top how we start with the input here, which is just all the images that we rectify. And then we have this feature extraction encoding with RegNet, bilinear FPNs, which are done to solve this encoding feature extraction task. And then we're going to have some fusion. So the fusion is done with a transformer network, and it's the idea that we want to fuse all the images together. And at some point, we're going to have then all the specific heads. So a head is one task. And so in my article, I did explain it this way, where you have as well like the images, but also the time fusion. So you have the queue with several images from before. And so you have the input, you have the encoder, and then you have the fusion, and then you have the head. So this is the HydraNet. And that was the 2021. And one thing to understand is that it's not Tesla's autopilot algorithm. It's just one piece and one piece of a larger puzzle where we have perception, localization, planning, control, and we could imagine that the HydroNet is solving maybe 80% of the perception task. Okay, so now if we simplify this architecture as Tesla simplified it, we have just these two elements: perception, which is about seeing what's around, and planning, which is about planning a trajectory based on what we see. So we kind of know perception, right? We know it's the HydroNet. Now, what about planning? And for Tesla's architecture, they talk about planning in three different ways. Number one was that they said, okay, there is A star. A star is like the source of planning. It's what most roboticists use. If you buy any robot and you start doing planning, it's going to use this algorithm. And the way it works is that you give it a heuristic, and so it's going to try and reach the objective in the shortest amount of steps. But for Teslas, for a simple parking problem, it's still 44K steps involved. Now, if you're working with A star and you also give it some navigation, some route, some objective, and the map and all of these, then you're going to reduce that by half. Okay, so you're still going to have a lot of steps, but you're going to reduce it to 22,000. And now the architecture that they actually use is what they call the Monte Carlo tree search. And basically in this architecture, they're just going to first have an estimation of all the possibilities, and then they're going to take it. And with that, we have like 300 steps. So I could say about this architecture, it's more explained in my post and even more in their video, but I could say basically that it's a classical approach that also uses a neural network as a combo. So it's like traditional technique plus neural network. And so basically, this explains the idea of planning. So when you're looking at Tesla in 21, you would see on the left it's vision, then it's two blocks in gray with planning, and the neural net planner and control together. So to understand it clearly, we have deep learning on the left and traditional plus deep learning on the right. Okay, so this is what we have. And that was up to 2021, 2022. And now they said at some point, okay, this is great, but we have an issue with that. And so, by the way, all of these images that I'm going to show here, they're all from Tesla AI 2021 and 2022 videos. So all credits to these videos. Now, they have issues here. Number one is here. They don't get overhanging obstacles. And this means that whenever they detect something, they use 3D bounding boxes. And the problem with that is that if you have an object like this one, like this excavator with specific shapes, you won't really understand it. You won't recognize it, so you won't have the shape. Number two is the 3D structure. So because you're in 2D, you lack 3D. So it makes sense, but basically you don't have the 3D understanding. Um, Number three is that you cannot see past some vehicles. So you're going to have an occlusion problem. Something's blocking, preventing you to see past that. And so the current Hydronet, even though it can understand the objects in 3D, it's not going to be able to really have that understanding of like all these, there is this object and then there is this object behind it and underneath there is another one and the pedestrian there. It's like a bit struggling. But the biggest problem is not even there. It's here. When you look at the horizon, you can see here that these pixels, like you have 1, 2, 3 pixels, maybe 10 pixels, they actually represent maybe 50 meters, right? Like a 50 square meter, like a big area with a lot of it. So it's actually a big problem because in an image, whatever is in front of you is going to be represented by a lot of pixels, and whatever is at the horizon is going to be represented by only 2 or 3 pixels. And that's a big problem because there is inconsistency in the depth. And so this is the final problem. So there is 4 problems that they're trying to solve here, which is the shape, the 2D, the occlusions, and the depth. And all these problems are somehow solved with Occupancy Network, which is the network that they release where they divide the space into voxels. So a voxel is like a 3D pixel, 3D cube. And then they assign a value to each voxel saying whether it's occupied or free. And so now saying this, they can say, well, here it's occupied, here it's free, so you can drive here but not there. And they created the Occupancy Network. Now, when you're looking at it, it looks like that. So it's a bit intimidating. And if I try to explain it from step to step, so I have, again, I have an article on the HydroNet, and I have a second article just on the Occupancy Network. Now, the step-by-step would be that we start with images, okay, like the surrounding images of the Tesla vehicle. And we go first to feature extraction for each image. So we're going to go with billionaire FPNs and regnets and all of that exactly as for the HydraNet. Now, at some point, we're going to introduce attention module. So attention is a concept where you're going to have query, key, and value. And basically, you're going to get occupancy features in 3D just for this specific thing. Now, I have an entire course on attention, but to explain visually what that would mean, imagine here we have query, key, and value, and we're trying to get the idea of attention. So this is from my former course, okay? And basically, see here how all the trees in the background are illuminating, okay? And this is because we have query and key going from this image, and we're saying, try to put your attention on this first block, which is all the tree on the top left corner. And basically, it's going to illuminate the all on this specific element. So what I want to say is that if you here have this here, this query being the first square, and you're multiplying it with a key, you're saying basically try to get this block here, which is the first element. And so try to find where the model, try to teach the model to focus its attention here. And basically that's what's going to happen. So you can learn the features, the relevant features using this, and you get also spatial and time attention probably. Now, you're going to fuse that with the occupancy features from T-1, T-2, and T-3. So this is here the time attention. And you coordinate everything, and now you get a 4D occupancy. And now it's the moment where I'm going to disappear, because now you're going to have two things: occupancy volume, which will give you basically occupancy but in 3D, and occupancy flow, which will tell you like whether the objects are going in front of you or behind you or in which direction, all of that. So it's a flow. Now, the actual architecture looks like this, and it's exactly what I just said. So it's images rectified, then RagNet, bilinear FPNs, then spatial attention, and then deconvolutions to upsample up to the original 3D volume. And this is what we get with an occupancy network. And now if we imagine that before we got like fixed rectangles shapes, now we're gonna get uh, these volumes which are either free or occupied. And so it's much better, right? We don't risk hitting anything that could like get in the way. Now, before this idea, we also had the idea of classifying whether there was an object or not, right? We had object detection. And if we missed, well, we missed. We had to catch that up with tracking. That was a problem. But now we just note that this thing, even if we did not uh, train for this specific element, well, this is an object, and so we know it as occupied. So if you had stuff that you did not, were not part of the data set, now you cannot be able to understand it. And the biggest element was also the 2D to 3D. So we had 2D bird eye view, now we have 3D occupancy bird eye view. So we are moving from a 2D grid to a 3D volume, okay? So this is what we have. And again, this is not a new replacing algorithm. It's an additional block, okay? The Hydronet stays, we still have it. It's exactly the same with the same ID, just that now we have the heads, and we also have this lane ID. So they added another extension of this network, where they're now treating lane line detection into the Hydronet, okay? So that's perception. Perception is two things: Hydronet plus enhanced view of lane lines plus occupancy. Now, what about the planning? And the planning is still the Monte Carlo stuff. And if I have to show you how it would work, imagine in this image where there is this pedestrian crossing, we must
Stay
fix.
slow initially, find the reasonable gap, we ended up and then finish the maneuver after all the. Stay slow
Okay, so I
initially,
was not
find the
planning it,
reasonable
but
gap,
that's
and
the
then
idea. You
finish the
have
maneuver
the
after all
pedestrian
the
crossing,
parts.
and then basically you need to yield to that pedestrian and also to a vehicle coming from the right. Now, the idea of the tree looks like that. You get the lane lines, the occupancy, and the moving objects at the first step, okay, at the output of perception. And you're sending this to the planner. And now the tree is going to say, okay, first we get the vision. Now we're going to get some goal candidates, okay? So we're going to say, okay, where are we gonna go? And next is like, we have that, and next is planning some trajectories, okay? So we're going to say, okay, should we go left? Should we go right? Blah, blah, blah. Now we say, okay, let's say we go left. What are our options? And our options are to either assert to this first pedestrian or to yield to him. So now we're saying, okay, let's say we yield. Okay, so we have this, and now we yield. And this is the final step, which is, okay, imagine we yield. What are the next options? And the next options are to assert to the vehicle coming from the right or to yield to him. And so again, we do that choice. So it's like, should we cross the street or not? Should we yield left or right? And then should we stop? And then what are the limitations and all that? And so we're going to have all sorts of like trajectories and possible options, okay, which are going to follow these steps. And now for each possible trajectory, we're going to select one, meaning we're going to generate maybe 20 trajectories. And then we're going to remove maybe 50% of them because they don't fit the tree. But then there's still going to be like 5 ways to yield to their pedestrian and the vehicle and to cross the street and to go to the left direction. And so these are going to be done with these classical trajectory scoring. So the collision checks, the comfort analysis, the interversion likelihood, and a human-like discriminator, meaning how close to a human being driver is it? So we have these 4 elements, and we need to understand that these are manually input into the vehicle. They're saying, if there is a stop sign, we need to stop for 3 seconds. This is what they're saying. And in an end-to-end way, it's going to be different because they're going to say, look at what people do during stop signs and do the same thing. And that's going to be a problem because nobody stops at stop signs. Um, so this is perception and planning. And if you're looking at the architecture in 2022 slash now, this is what they have in production today. They have occupancy network plus lane and object Hydronate, and that gives lane, object, occupancy to that planning and control module that is done with the Monte Carlo plus a neural network to speed up things. Okay, so we have 2021, 2022, and actually we also have 2023. But now, what about end-to-end? End-to-end is done differently. We have two key transitions. When you're talking about what's currently happening is a modular approach where we're going to have perception and then planning. And end-to-end, we'll need to have two key transitions. Number one is full deep learning, and number two is end-to-end. So let me explain you why these are different. If we're talking about full deep learning, currently we have traditional plus deep learning with Tesla. On the perception side, we have full deep learning, but on the right, the planning, we still have the tree search that is not really a deep learning stuff. It's more like we input manual rules and all of this. Now the transition, meaning we're going to need to convert that element to a deep neural network. So now a neural network will do the planning. Okay, and that was actually the first thing which was said during the decision to go to end was instead of manually giving the rules, we're going to ask the network to look at how others gave the rules before, how other drivers did, and now we're going to do the same. Okay, so that is the first transition, but that does not make it end-to-end if we're still having two modules. Now, end-to-end meaning we glue these models together, and now we're training with a common loss function, a common objective, and that is end-to-end. Now, the idea of this transition to this end-to-end training will be, how does it happen? And does it make it more of a black box? Because that's the biggest concern. So is it, do we convert the network to something we really cannot understand? Is it like we give it 10 million videos and now we're saying, okay, you just from these videos, take that to a model and then turn that into some sort of like just predicting how it drives and then you update the weights? Well, yes and no. Okay, yes and no. The misconception is that end-to-end network is just this, right? And so that's actually from my blog when I trying to explain end-to-end. So it's a misconception, but it's also a correct assumption, which is this is end-to-end. It's like input, model, output, and not input, model one, output, model two, output, model three, output, etc. It's like input, model, output. But it's not, this model is not just one network. It can be several, just that they are all glued together with a common loss function. So it can be these, and we can actually train separately. Okay, we could train this occupancy network, then this deep planner, then this Hydronate, and then have a final fine-tuning element where we train all of them together into some sort of loop. So what I'm trying to explain is that we could train a network to just create this occupancy, then train a network to create the deep planning and the Hydronate, just that we would need in the end a fine-tuning to get a common loss function. Okay, so from 10 million feed videos, we're going to select the ones that are correct, the ones where we have good driving, and that is a problem on itself because the biggest thing is data curation, right? The biggest thing here is like, how do we select the correct videos? How do we curate the videos? And from there, we're going to train. Okay, so I said nobody stops at stop sign. So it's the case for Tesla drivers, right? Okay, they're maybe even worse. So if they don't stop at stop sign, what does that mean? It means that we're going to either learn that or take a small sample of the people who stop at stop sign and just overtrain just on them. So now we have 10 million feet video, some training code, and then a model that is like that. And we can also have some subsamples, as I said, where we train some parts separately. We visualize, we verify that they are correct, that the occupancy is working as we expected, as it was in 2022, blah, blah, blah. Just that now, from there, we're going to train with a common loss function. Okay, so if we have this model, it's going to generate steering and acceleration, and then that's going to give us some steering and acceleration loss. And these two are going to be combined into some joint loss. Now, I had a question about it, which is, do we have a weighting factor? Do we have like, how does that work exactly? Well, we have labels. For every time we have a driving item, we also record the actual steering and acceleration loss. And we can also record tons of other things, which such as like how was the driver behaving, how much autopilot was involved, how much blah blah blah. Like we can record everything as labels and train and optimize all of these. Just that now we're gonna have acceleration and steering losses, and it's a joint loss in the end, and that loss is going to retropropagate, and now the update is going to be done on occupancy plus HydraNets plus planner all together, meaning it's not just the planner that generates steering and acceleration, is this entire block together, and the occupancy weights are going to be updated based on how bad the planner planned. Okay, so that's the biggest shift from traditional slash four pillars to end to end. Means that rather than having occupancy and HydraNets just train and optimized on finding elements and finding objects and all of that, they are now also optimized on how the planner then is going to predict the steering wheel and acceleration value. Okay, that is the biggest thing. Maybe I have to repeat this. Object detection is optimized based on how then the planning will happen. It's not object detection, okay, it's working, then planning, and now we optimize planning. It's like we optimize both of them based on how steering and acceleration are done. Okay, so this is what happens. So that is end-to-end training. This is what happens with end-to-end. And finally, I'm going to answer just 2 or 3 questions that I had that I did not answer here yet. Okay, so number 1 is someone excited that said, is it like behavioral cloning project? Now, I've been to the Udacity self-driving car nanodegree back in 2017, okay, and they had this fantastic project called Behavioral Cloning Project. And this project was fantastic because everybody on earth interested in self-driving cars tried at some point to reproduce it. And now every vehicle that you see that is like these small toys that are made autonomous, everything is based on that project. That is from the NVIDIA architecture in 2017, where they took a center camera, put this into a CNN, and then plugged that to a drive-by-wire interface that generated steering wheel and acceleration. Now, when you're looking at this was the project that I did back then. And basically, you could train a model, like if it's just steering wheel, to with a constant acceleration, to predict based on what it was looking at, to predict the steering angle. So you would say now it's going too much on the right, so let's predict a negative angle, and then too much on the left, and blah blah blah. So that was actually what was happening, and the goal was to train a network to do that, and then to try and generalize for other environments and all of that. So in your label, you had a steering angle being negative and positive, and you would actually record this steering angle. And the question is it the same thing? Is it like input CNN and then you predict this value? And the answer is yes. It's actually exactly that. We have some elements, the 10 million fleet videos, and every time we record some labels, which are steering wheel and acceleration, and probably more. And then we have a super complex model that I explained, which is done with the Hydronate and the occupancy and all of that. Just that now, we don't just predict the steering wheel and the acceleration, but we have also a deep planner that's going to predict trajectories and blah, blah, blah. And so we actually predict trajectories, not just steering and acceleration. We probably predict path forward and all of it. But rather than just 3 layers of convolutions, now we have something more complicated. Okay, second idea. What is my opinion on mobilized posts? So Who is Mobili? It's a startup that it's not a startup. It's a company that does um, autonomous driving slash ADAS to cars. And it was actually Tesla's first solution when they started autopilot. So they sold to Tesla some camera kits and they put it in some sort of in the mirror or in the front of the vehicle. And then basically Tesla used their algorithms to drive. And then they shifted. And now is Mobileye like Mobileye is saying that are we on the edge of a chat GPT moment for autonomous driving? And they're saying, well, uh, it still remains to be proven. So to show you the key part of the article from Mobileye that got released the same day on my article, basically, they said, first we have, is it sufficient and is it necessary? And for that, we're going to use three key elements, which are transparency and explainability, controllability, and performance. And they say like, uh, well, what speeds should we adapt on residential roads? Like, we're not going to encode any of that. We're just going to show drivers on residential roads. So is it good? Now, for transparency, they say it may be possible to steer an end-to-end system with regulatory rules based on like the data because we can overfeed some data, but that's still a problem. For controllability, it's an engineering nightmare. Okay, and also the performances of ChatGPT 4 deteriorate over time, and now we're basically trying to do the same thing, so we can have issues with that. And while it may be possible to use a huge amount of data, it's not proven that it's going to work. So taken together, we have concerns, and it's maybe overkill to use this approach. Maybe the rule thing could work really well, and that can be enough. And the idea to go from 300,000 lines of code to basically zero, because that's what happened. You don't have code, you just have input, model, output. That can be a problem. Now they're saying it's neither necessary nor sufficient for self-driving car systems. So what do I think of that? I think that's an opinion. And I think that it's a valid opinion. The concerns are great, although the engineering nightmare could be solved over time with other new innovations. And although we don't have experience on like Tesla's training at scale like they are doing now, we don't know because we didn't really test it on autonomous driving. Tesla has everything to prove here. They are saying we have this new breakthrough architecture. We want to believe them. We want to believe that's going to be possible. That still remains to be proven. When you're looking at Elon Musk live stream, the video is available on my article. When you're looking at their live stream, you're still having a disengagement after just 20 minutes. And that's because they drive at a traffic light that is red or something. And they're saying, well, this is why it's still not in production. It's still in test because we still have these issues. Okay, fine. I agree. I want to believe that. I'm a big fan of Tesla. Really, like that's everything they do. I love it. We're gonna still need to convince the public, the general public, everybody, that this thing is possible and that it's going to work at scale and that it's going to be made safe and all of that. So Tesla currently is at the bad spot of just having to everything to prove. And that's also where they are going to surprise every time, because every time they're going to prove something, everybody's going to say, wow, that's crazy. They proved that. And yes, they will prove it. And so I think I want to be positive. I also understand the concerns, which leads me to the third key point, which is, do you recommend learning end-to-end learning? Well, who does autonomous driving with end-to-end learning today? Tesla now, Wave, which is a startup in London, you should definitely look into them. And Comma.ai does that as well, and probably a few other startups. Now, you could learn it. If you want to find a job in autonomous driving, it's like, should you target less than 1% of the companies or 99%? I would recommend going with the 99%. Okay, so even if if you don't are in this job yet, okay, if you are not a self-driving car engineer yet. Now, if you work at Waymo and you want to move to Tesla, then maybe for sure you could try and learn how that works, and you can try and do some projects and all of it. But for the majority of people, I would say learn this separately, and even more because you see that these are just building upon the current architectures. They are not something conditionally new. It's like, well, we're just having Occupancy Network plugged with HydraNets, plugged with a new deep planner we're going to introduce. So basically, you still need to learn the occupancy and the HydraNets and all of that. Okay, so you could learn it for fun, understanding how to fit layers together, or doing the behavioral cloning projects, all of that won't necessarily make you a self-driving car engineer. Okay, so thank you for this short video, or maybe it's not short, I don't know. I have a lot more on thinkautonomous.ai, and if you are not in my daily emails yet, you're missing basically that every single day, okay? Plus a lot more, like career tips, insider stories, field stories from my personal experience in self-driving cars, breakdown of research papers and all of it. So really go to thinkautonomous.ai, join the email list, and I will see you tomorrow for your first email. Okay, thank you.